Dear students, already in the previous class we have discussed a property on Hamiltonian graph. Okay, again today in the session 12 we are going to discuss another property of Hamiltonian graph. So though there is no a general characterization for Hamiltonian graph so far, but there are necessary and sufficient conditions. In the previous class we have discussed one necessary and sufficient condition on Hamiltonian graphs. First of all, let me define one concept. Later on, we will discuss about the property. The neighborhood of a vertex. What do you mean by neighborhood of a vertex? Suppose if I take any graph G and let V be a vertex of a graph, okay, then the vertices which are adjacent with V are the neighborhood of the vertex V. That is, the set of all vertices adjacent to a vertex is called the neighborhood of V and is denoted by n of V. The following result gives a sufficient condition for Hamiltonian graphs. The theorem says if G is a graph with P greater than or equal to 3 vertices, such that for all pairs of distinct non-adjacent vertices U and V, degree of U plus degree of V is greater than or equal to P, then G is Hamiltonian. It implies a graph which satisfies this condition, then it will be a Hamiltonian graph. So this is one of the sufficient condition what we can say. Okay, a graph with the P greater than or equal to 3 vertices such that for all pairs of distinct non-adjacent vertices U and V, degree of U plus degree of V, if it is greater than or equal to P, then G is Hamiltonian. Let me take one example. Here we have considered a graph. Okay, so this graph contains 5 vertices, say V1, V2, V3, V4, V5. Okay, these are the vertices. Now in this graph, which are the non-adjacent vertices that you have to identify? Which are the non-adjacent vertices here? Here the non-adjacent vertices are V1 and V3 are non-adjacent. Similarly, V2 and V4 are non-adjacent, and V3 and V5 are also non-adjacent. Okay, now if we think the sum of the degrees of the non-adjacent vertices, for example, if I consider the degree of V1 plus degree of V3, that is 3 plus 2, so then it will be 5. Okay. Similarly, if I add the degrees of the vertices V2 and V4, so they are non-adjacent. So degree of V2 plus degree of V4. If you observe in the graph, you may see those things in the graph. Degree of V2 and degree of V4. So if you find the degree of addition of those two vertices, then it is 6. Similarly, if I consider the degree of V3 and V5, because they are non-adjacent vertices, then the degree of V3 is 2 in this graph, then degree of V5 is 3. Okay, so therefore it will be 5, right? So we have got the sum of the degrees of the non-adjacent vertices. So in these three cases, so these are the possible non-adjacent vertices. In these three cases, the sum of the degrees of the non-adjacent vertices either 5 or 6. It implies they are all greater than or equal to the number of vertices P equal to 5. It implies G satisfies the condition. Okay, so G satisfies the condition. When G satisfies this condition, then definitely G is Hamiltonian. If you see whether it is Hamiltonian or not, you can see there is a Hamiltonian cycle containing V1, V2, V3, V4, V5 and V1. So there is a cycle containing all vertices. Okay, so therefore G contains a Hamiltonian cycle C, V1, V2, V3, V4, V5. So it implies we have verified the result with this particular example. So let me try to prove the result. Okay, suppose the theorem is not true. So though the theorem is true, but what we are assuming, we are considering, suppose the theorem is not true, then there exists a maximal non-Hamiltonian graph G with P greater than or equal to 3 vertices, which satisfies the condition of the theorem. That is, G is Hamiltonian. But for any pair of non-adjacent vertices U and V in G, G plus UV is Hamiltonian. So this is because of our wrong assumption. We are considering the theorem is not true. Then there exists a maximal non-Hamiltonian graph, obviously with a p greater than or equal to 3 vertices, which satisfies the condition of the theorem. Okay, that is G is Hamiltonian. But for any pair of non-adjacent vertices U and V in G, G plus UV is Hamiltonian. Okay, since P greater than or equal to 3, G is not complete. Since G is non-Hamiltonian, each Hamiltonian cycle G plus UV, because U and V are non-adjacent. So if you join the graph G with the edge UV, contains the edge UV, obviously. Thus, G has a Hamiltonian path. So G has a Hamiltonian path P. So U equal to V1, say V2, and so on and so forth, Vp, which is equal to V. So our V1 is U and Vp is P. Now observe that if Vi, some arbitrary vertex Vi, belongs to the neighborhood of U, already we know what you mean by neighborhood of U. Okay, so neighborhood of U means those vertices which are adjacent with U generally. So now observe that if Vi belongs to neighborhood of U, then Vi does not belongs to neighborhood of V, because U and V are adjacent. Or else you just see the diagram here, figure. Okay, here we observe it starts with V1, next it is Vi, and so on and so forth. Yes, V1, Vi, and so on and so forth. It is Vi plus 1. So it will be Vp. Then we will come back like this. Then it will be Vi minus 1, then Vi minus 2, and so on and so forth. V2, V1. Okay, would be a Hamiltonian cycle in G. Okay, so therefore, what we can say, thus for each vertex adjacent to U, there is a vertex of capital V minus small v. Capital V is the set of vertices in G. So in that we are deleting V. So therefore, thus for each vertex adjacent to U, there is a vertex of V minus V, not adjacent to V. Then we see that degree of V is less than or equal to P minus 1 minus degree of U. Or we can say degree of U plus degree of V is less than or equal to P minus 1, which is a contradiction. Hence, the theorem follows. It implies, what is the theorem? Already it is Hamiltonian. When the graph satisfies that condition, it should be a Hamiltonian graph. But we have considered it is non-Hamiltonian. So that's why we got a contradiction. So it should be a Hamiltonian graph. So with this proof, we take one counter example to apply this result. Okay, so the example is, show that KNN, it is a complete bipartite graph. So complete bipartite graph means already it is possible to partition the vertex at V into two disjoint subsets V1 and V2. So it is KNN. It implies the vertex at V1 also contains n vertices. Similarly, the vertex at V2 also contains n vertices. Okay, so it is KNN, like K22, K33, K44, like that KNN. Show that the graph KNN is Hamiltonian for n greater than or equal to 2 vertices. So how to show this one? So solution. Let KNN be a complete bipartite graph with 2n vertices. It's very obvious. KNN is a complete bipartite graph. And what would be the sum of the vertices in KNN? Because V1 contains n vertices, V2 also contains n vertices. So totally 2n vertices. Okay, so the degree of every vertex in KNN is obviously n, because the vertex in V1 is adjacent with every vertex in V2. It implies the one vertex of V1 is adjacent with the n vertices in V2. So therefore, what we can say, the degree of every vertex in KNN is even. So, or you can say is n, not even, is n. Therefore, for every pair of non-adjacent vertices u and v, degree of u plus degree of v is 2n. Obviously, degree of u plus degree of v is 2n. Thus, by the previous theorem, so what the previous theorem suggests? If degree of u plus degree of v is less than or equal to p, here p is 2n. So, it is equal to 2n. So, therefore, by the previous theorem, what we can say, KNN is Hamiltonian. I hope you have followed this theorem with the counter example. So how we have applied the previous theorem. So therefore, in this session, what we did, we have discussed a sufficient condition for Hamiltonian graphs, and we have considered one simple example in this. So therefore, with this, so these are the books. If you want, you can refer. I have referred the group graph theory books by Frank Harari, so Narosa Publishing House, New Delhi, or you can refer the book Graph Theory by Professor V.R. Quilly, Vishwa International Publications, Gulbarga. So with this we conclude this session. Thank you.